Well, I guess it was following a couple of role models. There were no engineers in my parents' families, but I lived on my grandfather's estate with 11 cousins, and the older one was 15 years older than me, and when he graduated from high school, he decided he was going to go to college, and first one in the family so he decided to be a civil engineer. And I was about 4 or 5 years old at the time when he would come home visiting, and I was just so impressed with, he was wearing an Auburn ROTC uniform, and I thought that meant that was an engineer, so I told my mama, that's what I want to be, is an engineer like Bubba. And then the other role model was my older brother. My dad died when I was 8 years old, and so I had sort of a father model in my brother that was 7 years older. And so he also decided to go into engineering, and he became an electrical engineer. So I followed sort of in his footsteps, but I had a great interest. In addition to these role models, I had a great interest in building things as a kid, erector sets and tinker toys and everything you could think of in the way of building, and in particular airplanes. I was a fanatic model airplane builder, and so I guess there were symptoms that I could be prepared for an engineer. I love math, I love physics, and so all of those factors sort of went together that engineering just sort of seemed to be the natural with what I would like to do. Well, actually I was very, very fortunate the war was still hot, and so the draft board had already notified me to report for duty as I finished high school in '44. And the Army and Navy came around both with giving an exam, and they were looking for people that had apparently the background to be an engineering officer. And I took that exam and did very well on it, so I got selected. So I really, rather than going into the infantry or some other way, I actually went into the Navy, and it was equivalent like of Annapolis, except that we were located at engineering schools. In my case, I spent 16 months as an apprentice seaman at Lafayette, Louisiana, with an engineering school there, and then my group got moved to New Orleans, and we went to Tulane for 8 months. So I got about 2 years of, including in that was basic engineering training, as well as all of the things that I needed to learn specifically about the Navy and the ships and the communication systems and the engines and all of that. So I was really got a boost ahead in a way by my military duty. And I did go ahead when I went to Auburn and have a peacetime program of naval ROTC, and I took I entered that program and completed my requirements to be an officer. And so when I got my BS degree, I also got a commission as an ensign in the Navy, and I stayed in Naval Reserve for 10 years. And then, of course, my education, I did go on to Georgia Tech for a master's degree. And then my other connection with the Navy was my first job. When I finished at Georgia Tech, I had offers from the Navy in Panama City, Florida. They have a mine and torpedo countermeasures station there, and I interviewed there and was attracted to that job. So that's where I spent my first 3 years of my career also with the Navy as a civilian. Well, of course, my home is in central Alabama, Perry County, Marion. In fact, in my little community, the name of it is Highburger, which nobody ever heard of. But anyhow, I'm about halfway down the state, 65 miles south of Birmingham. But I was home for Christmas in '51, and I'd heard that things were happening in Huntsville, and that there was a team of Germans that had been moved here. So I was very interested, and so I called and made an appointment to come up while I was home for Christmas holidays, and came up and interviewed, and they offered me a job, and I did. I had some serious reservations because of the austerity of everything here. I mean, the German team had just been moved here, and of course the Redstone Arsenal was a munitions plant during the war, and what we had was Quonset huts and this temporary buildings was what we were going to operate out of in the early years, and so I was not impressed with the equipment of the laboratories, what labs they had, but so I thought it over for 3 months before I accepted, and then I decided it was worth a chance, and so I accepted the job and came up in March of '52, and that was the best decision I could have possibly made. Well, it was. Well, it's been a very interesting career. I wouldn't take anything really for the way it's all worked out. And my very close association with the Germans, so that was a highlight. There were 120 of them with Dr. von Braun. I claimed sometime to be number 121, but I wasn't quite that.
We'll give you the honor.
But I felt like I almost was a part of them, because there were so few of us Americans here when I hired in. And, but anyhow, I used to tell people that I'm a member of the von Braun team, and they said, well, you don't talk like the rest of them. And I said, well, I'm from southern Germany. So that's the reason my accent's a little different. I came in and got assigned to Dr. Walter Heuselmann's group, they called Control Section at that time. And so my first assignment was working on the control system of the Redstone, which was our very first rocket, very first precision-guided rocket. And it was, and the German team was moved here by the Army with the intention of developing a 200-mile range rocket, because the Russians had one. This is the way we were. It was a Cold War, and but anyhow, they got that assignment, and so I got involved in the details of defining the control system, and even working on the bench. We didn't have transistors back then, and vacuum tubes was what we had for the electronic system, but we didn't want to fly. I trust them to stand up to the environment of the rockets. So we were using a technique that was called magnetic amplifiers. It was sort of a simple, like transformers. It was something that hardly could fail. It was just wires wrapped around coils, and you could use it for adding and subtracting and distributing signals. And so I really worked on the bench, with magnetic amplifiers, and we used relays and the servo motors is what we drove the vanes to control the rocket, four servo motors. So I was involved in all of that. But in particular, I got involved into the simulation. We had a very large computer, about 6 feet high and 20 feet long.
Wow.
we did simulations of using the mathematic descriptions of the vehicle. We could program this computer and run test runs, and I really took a liking to that kind of field, and so I did spend probably about 2 years in the simulation lab, and but I was fortunate, we developed that rocket in just less than 2 years. We fired the first one in August of '53, and it worked. But that was my very early years, and then Dr. Horseman made me head of the control section, and he became head of the guidance control lab, I think it was called at that time. So I had only been here a couple of years when I got moved into a supervisory job, but it was only like a dozen of 15 engineers or something like that. But that was my very beginning, and Dr. Horseman was my mentor, and he taught me all I know, I guess.
Okay. All right.
So I stayed in essentially control from the very first day I came in, and we separate guidance and control, and the guidance group was a different group. We worked to go very closely together, but Dr. Horseman decided to combine the two organizations about 50, let's see, I guess it was in the early 50s, and I became the deputy director of the guidance and control group. So that was my first exposure to the guidance area, and really that's where I worked for the rest of my career, was really basically guidance and control. And of course in later years I did have responsibility for other electronic items, but as far as my personal contributions, technically they were principally in the guidance and control area, all the way right on through the Saturn and Skylab and everything else. Well, we didn't know that we were supposed to take 10 years to do something, or 20 years. It was emergency sort of thing for the Redstone, and then even more so for the Jupiter, which was intercontinental ballistic missile. In the mid-1950s, I guess maybe 54, intelligence indicated that the Russians had an intercontinental ballistic missile that was armed with an atomic warhead. And so Department of Defense panicked, you might say, and said, we just got to have one.
Right.
So what they did was assign to both the Army and the Air Force. By the way, all three agencies were competing for space as well as missile work. And then all three, and there was a lot of jealousy and contention between particularly the Air Force and the Army. But what the DOD decided to do is give both of us an assignment to develop one as quickly as possible, parallel, so if one of us didn't make it, the other one would.
Okay.
So that was our next big program, was the Jupiter, and we, I guess from the time we started on it in '56, we actually fired the first one of those within 2 years. But we also, this is getting ahead of God, but we did develop a modified redstone to use for nose cone research, which was required for the intercontinental ballistic missile.
Okay.
And the redstone, a short-range missile, you can have a metal nose cone and it will survive the re-entry, but the velocity that you're traveling, if you're on an intercontinental ballistic missile, would burn up a metal. So we had to have some kind of material. And so we modified a redstone so we could simulate with some upper stages the ballistic, the trajectory of intercontinental ballistic missile. So we did have an interim there.
Okay.
We did a Jupiter C, which was really just a redstone that was equipped so it could simulate the velocity re-entry that we needed to test these nose cones. Of course, you know, there's a lot of advancement in the electronic field. The things just are rapidly advancing. And the things we had to work with on the redstone, by the time we got to Jupiter, we were beginning to see the possibility of some use of transistors. We still avoided vacuum tubes, but we also avoided jumping at new technology if what we had was working. And an example of that was these magnetic amplifiers. They were ultra reliable, and even though we could have maybe upgraded that technology, we used magnetic amplifiers on the Jupiter and the Jupiter C because they could perform the function, and we knew they were reliability. So we did not always capitalize on the very latest thing. I mean, because if it wasn't proven technology that we could depend on, and of course we had all these environmental testing and everything we had to do. But we did begin to see a way to get out of some of the fairly crude things, like the magnetic amplifiers. What we had there was in Redstone was magnetic amplifiers, and then we had to amplify those signals with relays. We actually had relays. All we had, the system was magnetic amplifiers and relays and servo motor, you know. When we got to Jupiter, we had learned that you could use hydraulic actuators with a small valve that controlled the flow so that you could gimbal the engine. So that was the very beginning of the gimbal engine with the Jupiter. We decided we could, with two actuators, we could control the pitch and yaw angles, and then we could control roll with some little jets along the side. So we progressed not only in the electric field, but, well, with the electro-hydraulics. That was the first use of hydraulic systems to gimbal the engines. Well, that's a long story there. You know, we had the capability to launch the satellite before the Russians, but because of the internal politics and the assignments that have been given to the Navy to develop a separate rocket to put up a satellite, and of course, what we found at this little Jupiter C that we had used for the nose cones, we realized that if we just put this thing up to orbital altitude and use our 3 solid propelled stages on the top, we could put a satellite in orbit. So General Medeiros, who was head of our ABMA at that time, went to the Department of Defense, to the Secretary of Defense, and asked if we could have permission to put up satellite. And he said, no, Navy's got the assignment, and they're working on the Vanguard. So he came back and said, we got turned down, but build one anyhow and put it in the warehouse. Said they'll be calling on us. And that's a true story now. People think that was made up, but
Build it and put it in the warehouse. We're going to get the phone call.
he actually just defied his direction and came back and said, go ahead and equip one. They'll be calling on us. So that, I guess we were anxious that we could have put things up before the Russians did. So, I mean, it was a bitter competition with the Russians. They were obviously well ahead of us in space, but at least in propulsion systems, so they could put up much larger payloads. And it was a great surprise, though, to the nation. We all used to kid about them being technologically superior to Russians, but they were not in any sense. Now, they did not have in the electronic area. That's an area where we were ahead of them, and but in the propulsion area, they had spent a lot of time and effort expanding on their propulsion. You know, they captured some of the Germans too, who had rocket background, and particularly some of the propulsions. So they were definitely ahead of us, and it was. They put up a much larger payload with their Explorer, with their what was it called? The Sputnik. The Sputnik. They put up about a 250-pound payload, and the best we could do with our little Redstone was about a 50-pound payload. But and it was morale. It was a big boost.
Okay.
That we just 3 months after they put up one, we put up satellite. We could have done it quicker because it was already in the warehouse, but we couldn't reveal that to the Department of Defense. We had to pretend. Von Braun said 60 days, and Medeiros said no, 90 days, because 90 he had his neck out. You know, he had authorized. Not with in a direct opposite of his command from his leader. He reported directly to the Secretary of Defense, by the way. That was one improvement they made in Huntsville, in that we were when they gave us the Jupiter assignment, they elevated us from, we were called a guided missile development division. Well, they made us an agency, Army Ballistic Missile Agency, and brought in Medeiros, a 3-star general, and he reported directly to the Secretary of Defense so they could expedite our job, to be sure we got this rocket built quick as possible. And we did. We did it in 2 years, and at the same time, the Air Force was having all kinds of difficulties. Their Thors were failing at a rate of about 70% of test flights. So, but anyhow, we were fortunate to have the leadership that we had, the technical leadership, and we were really the best. I mean, I just have to admit to it.
And by this time, you had better facilities, right?
Right. Oh, by all means. When Medeiros was sent here, and we were supposed to go all out, full speed, hire whoever you need, how many you need, build whatever you need. It was unlimited. That was two times that, and then the moon program or two, where we didn't have to worry about resources. I mean, they needed that intercontinental ballistic missile as soon as possible, and we got them one. It was different in that this was the first time we would be endangering a human being's life. And it was, well, we took all of this seriously, but this just added another exclamation point to it. And there were some people, even in the technical areas and even in some of the German leaders, thought that this was just a stunt, that we wasn't gaining it. We wasn't going to be able to put him around the Earth. All we were, the Geophysical Society has defined space as being 100 miles high. If you could put an object of 100 miles high, it was equivalent to being in space. So we had the capability with the Redstone, except we had to elongate it. We had to make it longer, and of course that meant redesigning to some extent the control systems, things like this. So it was, but of course it was, I mean, we just, in all seriousness, we just did everything we could to make it reliable. The Redstone had proven to be by far the most reliable rocket built to its time, so it was used for a variety of things, both military as well as space. And it was the only rocket that I guess anyone was able to feel safe with putting a man on. But we had, the Army, they wanted to verify not only the reliability but the accuracy of the Redstone. I'm going back to the first half of the 50th century. And we fired about 30 or 35 rockets just to prove it wasn't by chance we could fire one or two or three and they'd be successful. So we had full confidence, but at the same time, you have that knowing thought, what if one of those little things goes wrong, you know? It's so it was, I guess we were as careful as we could possibly be. We did not have the capacity then, though, to carry long redundant systems like we later did on the Saturn. But so this was all simplex. We had a lot of what you call single point failures that could have, because we spent a lot of time on the escape system too. We had an escape system. You notice every rocket that we were ever involved in that had a man on board has a escape rocket on top of it. Now, when I say involved in, and the exception is Shuttle, but we didn't control that. Oh, well, we took great pride in that. I mean, but in all honesty, it was a little bit of a setback in that the Russians had just put up their first man in orbit 3 weeks ahead, 3 or 4 weeks, probably not by coincidence, because they knew everything we were doing. And I guess even though we were elated, certainly that we were able to do that and to show you could bring a man back safely and let him drop in the water and save him. Now, we did have a little hiccup there. There was some danger there that the hatch was leaking at Alan Shepard's, and there was some concern that if we had delayed, we might have had a catastrophic situation. But the ships were able to get to him in a hurry and get him out, even though the capsule was leaking. So, and so that technique now was used right on through the Saturn program. I mean, so that was the first step, showing that there was a way you could land in water and safely recover, and of course also that you could parachute down a spacecraft so it wouldn't burn up and whatever. Right. So it was a major step forward, even though it, compared to the Russians, it was a sort of a minor thing, you know, because they were obviously, as I say, still well ahead of us. You know, that was unexpected, and that is a major, very major step forward to go from where we were. You realize this was only about a month after Alan Shepard's flight, which all we had been able to do is lob shot up there and travel a short distance and then drop in the water. And the president comes along and says we're going to go to the moon and bring a man back alive. I mean, there was, I'd say, consternation on the part of a lot of technical folks like me. Like, how are we going to do that? And Von Braun's out dancing in the street, you know. He you know that term that he has about dancing in the street. Inside, he was dancing in the street. You know, he actually, President Kennedy, before he made that announcement, even though they had had several inputs from people as to what could we do to show we go technologically superior to the Russians, he apparently relied on Von Braun more than you could imagine. I understand he called him before he made that announcement. Are you really sure we can do this? And Von Braun said yes. Well, as Von Braun's daughter said the other day, he was the eternal optimist, you know. She was speaking, I don't know whether you heard her speak or not, but she said he was up every morning that everything would go right today, you know. So, but anyhow, you know, we went pretty quickly from like wondering, well, how are we going to do it? Well, we better get on with it.
Right.
So, because he'd already used 1 year of this decade, you know, when he announced it. We only had 9 years.
Right. How many years do we have left to do this?
Right.
And now that just seems like such a short time period. That's what stands out to me.
Well, you know, I guess the fact that you have a leader with the optimism and the capability of Dr. Von Braun, I mean, everybody just turned to and said, yes, we can do it. If he said we can, we'll do it. And, but it was just a pleasure to be involved with that kind of attitude. I don't think Dr. Von Braun ever doubted that we could put man on the moon and bring him back, you know. But when a lot of people then working the details, you know, like it's a lot to do. And then the Apollo program was very logically laid out. You know, people wonder, well, why'd you have to use 12 Saturns, you know, to go to the moon? Just put one crew on the moon. But we went through, you know, the Saturn 1 and 1B as test vehicles, and we gradually, we developed everything. And we made extensive use of putting hardware and the crew in Earth orbit to test before we went out of Earth orbit to the moon. So there was a logical sequence, one little step at a time, you know. It's or maybe some giant leaps through with
Giant leaps in that sequence for sure.
Yeah. There was a natural progression all the way from the Redstone. You can trace it. What we learned on Redstone, we used on Jupiter, even though we used some new techniques if they were available and proven. And then when we went to the test vehicles for the Saturn V, the Saturn 1B, 1 and 1B, we used, we actually used a lot of the, you know, the first stage of the Saturn 1 and 1B was a cluster of a Jupiter with 8 redstones wrapped around it. So that's just the example of how we use the past rather than designing new tanks. We use that technique. So you can trace a progression in some of the instances all the way back to the Jupiter and even to the Redstone, like the gimbling of the engines. And then when we went to the Saturn 1, that's when we first had multiple engines on the first stage, and we learned to gimbal, for the 4-out engines before we went to the Saturn V. So it was a logical progression, although we, much of the same techniques that we used, like on Redstone and Jupiter, are carried right on through to Saturn V. And an example of that is the famous magnetic amplifiers that I mentioned. I was working on them in 1952 on the bench. We sent man to the moon with magnetic amplifiers, controlling the signals to those engines. So even though we incorporated new technology as required, if we didn't require it, we wouldn't touch it.
Okay.
Dr. Haldeman used to say, avoid new technology like the plague. Don't do it unless you have to. Well, actually, it's gratifying. I mean, every step of the way. I mean, well, and here again, we took this one step at a time. We didn't allow the astronauts to fly the Saturn V nor the Saturn 1 or 1B. We had that all totally automated, controlled by computers. So we were able to put crew and hardware in Earth orbit, both with the Saturn 1B, to do testing. Before we didn't have to use the crews to start with. We could put an totally automated system. So the first big step as far as the final proof that we could do it with the Saturn V was when we launched the Apollo 5. That was the first automated system. So we actually went into Earth orbit and back without a man involved. And we ended up launching 2 of those. So that's what I was speaking, that the way the program was laid out, it was like one step at a time, and then go into Earth orbit and test all of the equipment that went to the moon. We went through simulation in Earth orbit before all those things that are going to happen, going down to the moon. They couldn't simulate it exactly, but by being in 0G, you could essentially simulate the conditions that they were going to see on the moon. So all of these steps were one at a time. But yes, as far as technology is concerned, we incorporated it where we needed to, but like just the example of gimbaling the engines, we went to these hydraulic actuators, and that turned out to be a very successful way to provide a very large force. And all we did for Saturn V, we just made the actuators larger. they had each one of those actuators on that gimbals, the big engines on first stage, has a force of 50,000 pounds. Well, we didn't need but much less than that on the Jupiter. So we had actuators with maybe a diameter of maybe 3 inches, and on the Saturn V we just went to much larger. So we just upgraded things and increased the size or whatever, but still used the same technique. So the techniques we did on Jupiter for controlling, all that was carried through the Saturn V. Well, of course, there are many highlights along the way that I remember. Certainly the first automated system to Saturn V, that was a major step forward, that we really can do this with a computer and without any outside influence. We don't have to send any radio signals or anything else. It's all pre-programmed, and that was the first major step. And of course, there, as far as the Saturn program was concerned, there were several highlights. I think going around the moon was one of the most gratifying moments. This is the first time that we had put a crew on the Saturn V, for one thing. This was one place that we violated our principle that you got to go one step at a time. But Dr. Miller, our leader in Washington, decided that we were not going to make it in the decade if we completed the complete program as laid out. So this was rather, the Apollo 8 was somewhat of a controversial thing that we had intended just to put the crew in Earth orbit first time. But Dr. Miller insisted that we're not going to make it if we don't cut something. So the fact we put the crew on the Saturn, first time Saturn V, and sent them not only into Earth orbit, but around the moon. And this was controversial in that, well, some people say we're taking an undue risk on the lives of 3 people just to be sure we stay within the decade. But that was a decision that was made, and we did it. But, you know, and actually the way they handled things too, the first crew, you know, Frank Borman and the photo they sent back, you know, looking back to the Earth, where I knew for the first time Earth's really round, you know.
Right.
And it's got water and it's got ground, and then they read from Genesis, in the beginning God created heavens and the earth. And you know, while they are seeing this, we were seeing all this for the first time. That was one of the highlights, I would say, in my career, was that Apollo 8. It even stands right almost parallel to landing on the moon. You know, I just.
It was such a first.
Yep.
It was another first.
Yeah, another first.
Humans had ever been out there and ever shared that view.
Oh, that's right. No, that's one of the first there. You know, even though it was, you know, we had put on Apollo 10, we put a crew almost down to the Earth's surface to be sure that it would work to come back and rendezvous in lunar orbit. So we put one crew almost to the Earth's surface and to check out everything, you know. So there again, it was a little one step at a time. But the actual landing and getting out and walking around, that was, of course, well, the most important event, I guess. It was development of the launch vehicle digital computer. The launch vehicle digital computer.
Okay.
This was a giant step forward. We had never flown a digital computer. Nobody had ever flown a digital computer. And analog systems they're much simpler, and that's the technique that we used. And I won't try to describe the difference, but digital computers are much more complex. But in the Saturn V, and we were able to use analog computers on everything up to the actual Saturn V. And so we did use a digital computer on the 1B also, but we in-house had designed typically everything that was in the instrument unit. I mean, even though it didn't appear as an instrument unit in the earlier vehicles, I mean, we didn't have the same ring situation, but all the communications and the instrumentation and the power systems and everything, we had them. We had examples of that, had experience with them, and so what we did was always develop in the first and build the first maybe 2 or 3 of whatever it was, transmitters or transponders or whatever. But when we got to the Saturn V, we realized that we can no longer use analog techniques, and we've got to have the capacity of a digital computer. Digital computers were being used extensively already in business applications, and And we were even using them in some of our test applications, but nothing had been built that was considered flight worthy. So this was a big problem to us, and we had experts in all of these areas, except we were probably very weakest in digital computers, even though some of our people had a background because they were using them for business purposes. So that was a challenge, and we decided, hey, we got to depart from this thing of doing everything in-house, and we've got to bring in experts. And so we made a survey. I well remember with myself and Ludi Richard and Norm Gelino went out searching around to see what was available in the digital world where there might be some adaptability for flight systems. And we had heard that IBM was developing a flight computer for the Air Force, and so we visited them in Wego, New York, and we were impressed with their capability, and they were concentrating on miniaturizing and ruggedizing so you could use something. So we ended up with giving them a contract to join us, and but that was a massive development, and of course we were very heavily involved. Our engineers spent many days going back and forth to Wego, New York, and having the crew to come here. But that turned out to be I'd say the most difficult and probably one of the most expensive things was developing that digital computer, and it's rather crude by current standards. You know, I mean, we had used we didn't have anything even approaching micro miniaturization, not even miniaturization. We used our little iron cores for the memory, and we had all the capacity of 500,000 bits of data was all we had in that computer. And people laugh at us that we were able to do anything with 500,000 bits, you know. And but anyhow, that was, and adapting that and using it, incorporating it, all of that. Of course, we had to do that, so it wasn't only developing the computer, but and the software. We did bring IBM to help us with the software development also. But I'd say that was the single most. Most of the other stuff was an evolution. Like the other key element of the guidance control is what we call a stabilized platform. It's a gyro control plate that you stabilize at the launch site, and it stays space direction fixed all the way to the moon. And so the rocket rotates around it. We get the signals that we feed to the control system to keep it flying straight. Okay. And we had on board, and this is getting maybe too technical, accelerometers, which we know which way pitch or roll is, because it's still exactly like it was on the launch site. And we can, if the vehicle translates to the left or the right, we can send a signal to the gimbal engines and bring it back on course. So, but that stabilized platform was the outgrowth of everything all the way back to the Redstone. We had an excellent group of people. We had a separate laboratory, as we called it, the Gyro Lab. We had a guidance control and instrumentation and the communication, but we also had a lab that focused the experts specifically on that stabilized platform. And that stabilized platform was the secret to all of our successes as far as accuracies of our vehicle. We were far ahead of everybody else because of the techniques that we had. What we called the ST-80 was what flew on Redstone, and then the Gyro Lab people upgraded it and made it somewhat smaller in size for the Jupiter. So we flew at ST-90, and then we had built an ST-120 to fly on the Pershing. I haven't mentioned Pershing because it was not used in the space program. It was a military strictly.
Okay.
But then we took the Pershing platform and put an extra gimbal on it, and we were able to use it for the ST-124, which is on display in the instrument unit, and it is what flew in the instrument unit. So that's another piece of very complex equipment. But in that case, we had the in-depth expertise, and it was just a orderly progression to go to the requirements of that. But you know, there were, of course, other challenges, but I'd say incorporating and knowing how to use and evaluating the digital computer, that was probably the most challenging part. You know, my quote, that's even part of it, is on the on the one of the displays over there that that I said, if I tease my propulsion structures people, that, you know, if it wasn't for the IU, it would be just a big dumb booster sitting on the pad. It wouldn't know where it was, where it's supposed to go, nor how to get there.
Right. You made the rocket smart.
Right. They make a lot of noise and fire and everything, but
Right.
depend on the IU. But I do get along well with my structures and propulsion friends, but I do mention that occasionally.
Yeah, you gotta kind of get those little jabs in here and there.
Well, it's the key with gyros. The key is trying to have frictionless motion, so the gyro doesn't get torqued because of friction. And what the Germans came up with was air bearings, they call it. You were floating. You had holes in two cylinders, and you were essentially floating on air,
Okay.
on the molecules of air, very, very thin. And so they were able to get phenomenal accuracies with their gyro. I think that we had like 100th of a degree per hour drift, which was far aboard what we need. You know, we only had our flight time flight time to Earth orbit is only about 15 minutes, and then we spent 2 orbits there letting the astronauts check out their systems before we reignited the 3rd stage and sent them and increased the velocity so we could escape Earth's gravity. But that total time, you know, it's 3 hours in orbit, but it's about a total of 4 hours at the most that we had to have. So this minor drift, like for Saturn, it was insignificant, and it's all the way back to the Redstone. With the Redstone, we could hit a target of within the length of a football field at 200 miles, which was pretty good back then.
I'd say so.
Well, you know, that I'd say that's just the situation there that we felt that we were stepping ahead of what our experience had told us to take one step at a time. We started to take a giant leap, you know, and that's but that was controversial. But other than that, you know, I think, you know, even the launch of the first crew to the moon, you know, went very smoothly. I was at their launch site, by the way. I had the good fortune of being there, and well, we had 2 control rooms. One, we have the engineers that got all these panels and everything, and then there's a second control room where we managers that can't contribute sat, you know. So I was able to be there to wave goodbye to them anyhow.
Yeah.
And it was a highlight, the landing on the moon. I didn't feel like even, we had all sorts of celebrations in Huntsville when they landed on the moon, and parties, and I got invited to several, and I didn't feel like I wanted to do it. I said, I'm still uptight. We haven't got them back yet. And so I always say, well, my celebration occurred when the parachutes opened, when I saw the 3 parachutes on TV that they were on the way back in the command module. But it was, this is an unforgettable experience, I guess. This is pure and simple. And the fact that, we were able to put all of the other crews on the moon. We had some excitement along the way, though. We got, when we got struck by lightning on Apollo 12, the second flight. And our system ignored it. It's amazing that we're not fully understand yet why when we got struck by lightning, everything in the cockpit, all the instrumentation went crazy. And, the lights went out and they were in the dark, and we just flew right on through it without a blip because the computer was in charge, and using this platform. But none of that hardware in that loop, the computer and the platform and the analog computer that drives the engines and all that, none of it showed any evidence of knowing that we got struck by lightning. And that crew in particular, and that was the second crew to go through, that was, Pete Conrad and Alan Bean. They were the 2 that landed. They were 2 that came and thanked us profusely later for not letting them control that thing, because they would have lost control. We don't know whether we would have made it through or not. And we had one success, and then we had Apollo 12, which could have been a disaster. And then we had Apollo 13. And I'm not sure that the program would have continued if we had lost the crew or had a catastrophic failure that they had to abort on 12, and then 13 with those problems, whether the program would have continued or not. We had put a man on the moon. That's what Kennedy said. He didn't say we're going to put 12 on the moon.
Right.
So
there was a bit of uncertainty during that time period.
So I guess that was just one example that our system, and another was we on the second unmanned launch, 2 engines went out on the second stage, and our system adapted to that. It guided and controlled it, so it still hit the target. But what it had to do was, rather than the second stage burning 6 minutes, it had to burn for about 9.5. But the computer knew to do this.
And it adapted.
So we claim we saved probably two missions by the computer system that we had.
That's amazing. That's really awesome.
Well, now that and the way that came about, the same team, Von Braun had about 12 or 15 very senior, high technical people that were the directors of the laboratories, is what it was called, the propulsion structures, guidance control, air ballistics, test, launch, even had the launch capability here, Dr. Devers. And that same group that was in the senior positions when I came here, they were still in those positions in going into the last of the 60s. Dr. Horseman was one example that he just got moved to a different function. Dr. Haldeman, I was the head of the Guys Control Division for the first 8 years of the program, 7 years, I guess. And then Dr. Haldeman, they decided we needed a system engineering group, and Von Braun prevailed on his senior people to, one of you got to take it, and well, I don't think any of them wanted to. All of them were specialists in their technical area, and they weren't interested in getting into some overview. But Dr. Haldeman finally agreed to take it, and but he, and I don't know how I stood out in his mind, because I would not have selected me, but he selected me to be the Astrionics Lab director, and so I became director of the whole, all of the communication, instrumentation, and the power systems, and everything that's in the IU.
Okay.
But my first, where I was heavily involved, was the division chief, was about the first seven years. I had about 100 and something engineers and technicians, and the Astrionics Lab was. It was like 600 engineers, technicians, and personnel. But I became director of that, and again, it ain't bragging, but I was the only non-German lab director. I mean, for those last 5 years, and that was a great enjoyment to me, because, well, I say I enjoyed very much association with the whole team, as a matter of fact. But Dr. Haldeman was my mentor, and he's the one that brought me along, and like I say, even gave me a laboratory, which I wouldn't have had otherwise. The change in organization at the end of the Apollo program, that was a downsizing of the whole operation, and we used the Saturn launch vehicle to put Skylab up. So we were still using the Saturn first 2 stages to put the 3rd stage in orbit.
Okay.
But we did have a reorganization in that time, and they downsized the laboratories. So that's when they did some reorganization and renaming, and my laboratory was then named Electronics and Control.
Okay.
And that is, I guess that time frame was probably right around the time frame of Skylab's development. And so actually, I still had the control responsibility, and the Skylab was, it was brand new, plowing new ground too. It's putting up a body that would stay in space for that period of time,
Then it would be this area where they could live and work, and
Right,
was supposed to stay
right.
there.
So we had, there was some unique, certainly things there. One is how to keep the body that's in orbit stabilized, and over a long period of time. What we had done on all previous programs, we used propulsion systems. I mean, either gimbling the engine, or if you needed roll control and only had one engine, you had little jets on the side, and that's what that's what the S4B stage, the one that had, that's the way it was laid out. It had these little jets to keep it trying. The problem with that is if you got long duration, you got to have a way to take the fuel along for 30 days, 60 days, or 90 days. So we were faced with coming up with some means of controlling the vehicle in orbit over long periods. And that's where we took a giant leap into another technology which we call control moment gyros. Langley Research Center had been working on using gyros to actually put a force on the body itself. And that means rather than the little bitty gyros like that, the wheels were like this, I mean literally. And they had done some research on it, and we got with them and jointly just figured whether we could actually adapt that to the Skylab, and we did. I mean, we actually adapted that, and we used 3 huge control moment gyros to control the Skylab to keep it flying pitch on roll. So, and that worked out very well. I mean, we were able to, do all 3 missions. It's 30 days, 60 days, and 90 days. And there again, this was a step process of, how long can man stay in space without some severe adverse reaction or so. And so it was a step at a time. We did 30 days, and everybody came back okay. 60 days, same way, 90. So, and I guess I'd say Skylab was really very significant in that it was the first time that we had proven that you could have man operate in space over a long period of time. And some of the techniques that we developed, the exercise machines and all those different ideas, the showers and how everything that we did on Skylab, a lot of that, at least the basic principles were carried forth into the International Space Station. And it's regrettable that we didn't keep Skylab up, and that is another story. And that's, I think NASA made a serious mistake. We could have, in fact, we had designed a little teleoperator retrieval system that we could send up and dock to Skylab to reboost it like every 2-3 years if we needed. And when the severe budget cuts came after Apollo, there was a strong tendency to put everything in shuttle. And that's what we did. We put everything in shuttle, and even this little teleoperator retrieval program got canceled. And eventually, as any other body does, the Skylab decayed with time until, it finally re-entered about, I guess, 6-7 years later. But it could have been the foundation for the international, what is now called the International Space Station. We could have had it many years earlier. There's a big gap in there, but the time to Skylab, and when you put up the first modules of the space station, So I think Skylab, the technology contributed to to the space station. It's just that I have argument with that we made a mistake. I think NASA did to put everything in shuttle, as wonderful as it was and everything and all that it did. We flew shuttles for 30 years. I think we could have gotten by with 15 and used some of that money for new propulsion systems, for instance. I mean, we didn't develop an engine. We are now depending on the Russians, of all things, to put us up to the space station, because we did not develop a darn thing from the time from the F1 engine and the J2 engines until we put all the money in shuttle. But that's just my observation. Yeah. I stayed with the government through the second shuttle launch, and so I was involved in the shuttle to the extent that that anything electrical, electronic was involved. Now, there was one distinct difference on the shuttle: the guidance and the computers to do the overall controlling are in the orbiter. And so it was not the responsibility of Marshall. Marshall's, so my main responsibilities in the shuttle were related to the solid rocket booster, which we used for control. So we had the gimbal, same way with the solids that we did with the liquids on the other vehicles. So all of the control itself, but not the guidance, we would do it internally within the solid rocket boosters. And also we had one other major change in that the liquid engines on the shuttle are so complex that we had to have a digital computer actually as a part of the control of that engine. Because Marshall had the propulsion they had the responsibility for the propulsion system, so the electronic part of that was part of my responsibility. So developing those computers and testing them and utilizing them, that plus the control of the solid rocket booster was the primary contribution that we had to to have a digital computer on a live engine with all the vibration, that was quite a challenge. But we did, like I say, we did go through the design phase, and I was with the government through the first 2 flights, and then I went. I spent three years at Teledyne Brown working on a military program. Then I joined a little company, Control Dynamics company, and which a couple of my friends had started, and they were focusing on guidance, nav, and control, my area, and so I joined them, and I spent 25 years with the company.
All right.
It changed hands several times. My name's still on the roll for my two friends, both PhDs. One was a structural dynamicist, and the other was a control type, Dr. Seltzer and Dr. Worley. And they built this little company out of just high tech for the purpose of doing high tech technology. So I was working back with Marshall during much of that 25 years that I spent with them. But the company got bought by Logicon, so we were a division of Logicon, and then they sold us to BD Systems, and we spent 10 years with BD Systems and became a part of SAIC.
Okay.
So you hear that name, and of course the name you're beginning to see pop up is Leidos. Right. Leidos was a split of SAIC, literally, and our local group, which has about 50 employees, became a part of the Leidos portion. Most of the local SAIC, they have by far the largest. They got a couple of thousand people, local. Leidos has, now they're building up. I think they've got about 250 now, but they keep my name on the roll, but I'm not as a senior advisor. I tell him the senior part's right. I don't know about the advice.
Well, that way they can call you when they have any questions,
But they still got my name on the roll. But I do very little. I can visit them occasionally, locally, just to keep in touch. In the very beginning, we called it Large Space Telescope. You know, we had a program development operation here that was looking for other ways, other things, other than propulsion and launch vehicles, and we got heavily involved in those early years of design. One thing, not only did we have the guidance control problems. One is controlling the body itself, and the other is the precision pointing systems. So in the very early years, we did a considerable amount of research and testing and supporting the concept development before it even became Hubble. It was called Large Space Telescope. And then we got into the implementation phase. We were still involved. By the way, I had in my lab an optical group. That was maybe a little bit of anomaly to the guidance control area, but we had that was an assignment we got, and so we had some really key experts in optics, and they were heavily involved in the early days of design of the vehicle from an optical standpoint. And we actually were involved, I hate to tell you, but you know the mirror was ground. Are you familiar with the catastrophe in Hubble?
Oh.
That the main mirror was ground with an error?
Okay.
Well, that happened to have been my responsibility, but we had a real controversy about the contractor that was picked. And I relied on my Dr. Joe Randall, and Gene, let's see about his name, but had a deputy. But they had a functional optical operation, and if they had been allowed to continue, I think they would have prevented that. The end result was that when Hubble got on orbit, it was not precise at all in its optical, in that there was a little flaw in the way the thing was designed. We're talking about, about a 6-7 foot mirror, 8 foot, I've forgotten what, 8 feet, I guess. I saw it myself being ground, but I couldn't tell you anything about whether it's doing right or not. Right. The only thing, the saving grace was it was precisely ground to the wrong exact shape, and we knew what that was. So what the solution was finally was to, as they say, put glasses on the telescope. We sent the astronauts up and put another lens in series with the optical chain, so that it corrected for that little error that we had. So then, from then on, we've just got remarkable pictures. By the time we got around to actually flying the Hubble, I was no longer with Marshall, certainly, and. So I wasn't involved in a day-to-day basis on the final development. I was with mostly the early phases, and of course it took a long time, to come up with a correction, but no. And I was not personally involved in that as far as this concept of putting glasses on it, you might say. That actually was. I guess, like I say, they sort of transferred responsibility to Goddard. But as far as the Space Telescope is concerned, I think the finding the Space Telescope is, except for, let's say it doesn't parallel the landing on the moon as far as drama, but as far as actual knowledge, Space Telescope is the thing that has exposed what the universe really is. And it's pretty big and growing. And so I would say the Space Telescope is one of NASA's major contributions, really even more so than going to the moon. That was a stunt, by the way, just to prove we were technologically superior. We didn't go after rocks, as people think. We brought back a bunch of rocks. But I think that was a facade. I'm not being facetious about that, but I would, as far as I'm very enthusiastic about and proud of the fact that I was involved in the very early phases and made certain decisions, like the experience we gained on Skylab with that control moment gyro. We used those on telescope. So this again was a progression sort of thing, just like the Saturn program. We had proven control moment gyros, and that was a satisfactory means of control, for the body in space. And so that same essentially technique was used on telescope.
Okay, that's interesting that those two are tied together too.
Right.
So
Again, it's just a heritage thing. Right. The legacy. Well, I guess we've got a lot of experience on what to do and what not to do. I think this philosophy that we had for ultra-conservatism, over-design everything, like we grossly over-designed the Saturn reliability system. We had triple modular redundant on some systems, and we never had even a single failure on any. And we never had to switch to the backup, Some people say, well, you over-designed, but we're proud of that. We over-designed. But I think being ultra-conservative and being extremely careful on the incorporation of new technology and a continuity of development from one thing to the other. I mean, that's just the experience that I would say that had a key role in our success. Otherwise, the emphasis on teamwork. Dr. Von Braun insisted that we be called a team. He insisted not being the difference in German heritage and American heritage. Well, we were all Americans, but they joined the citizenship. But he made major emphasis that we are a team, and I think that philosophy has carried through, and we had such a good, close, and cooperative relationship with all the other technical areas. We didn't even have what you call system engineering until they set Dr. Horseman up. We just knew each other and we worked together. I mean, and that worked very well. But I think one of the main things is to learn to deal with each other and across disciplines and support each other. And, the camaraderie that we develop is still evident in the local community. In fact, we got 300 or so people signed up for the Marshall Retiree Association. We have these socials, and the fact we are volunteering right here. This is part of the function that, and of course, I never miss a social event. The space group, and let's see, I meet 4 different groups for breakfast. So
that's great.
Once a month, and then we have our Marshall Retiree socials, and then we have all these other big events that but I think the camaraderie is, well, that to me is one of the most rewarding aspects, and I don't know how to say, but I think that you need to work at that. You need to realize whatever you do, be a member of the team, and don't take credit for anything. Just pass it on. You know, Dr. Von Braun's his concept, and I tried to pick it up in my laboratory too, was that we're all equal. You know, he doesn't believe in the pyramid, so I said, well, his concept is like you remember the old records that used to spin around and you had a little hole in the middle? Well, he believes we're all equal, you know, with the little bit of leader maybe in the middle of a little blip. And I think association with each other and mutual respect, that's probably is more important than technical insight. Getting along with people. Love each other.
I love it. That's wonderful. I think that's a great takeaway. And I think that's part of why the program was so successful.
I think so. I think it really was. I think that was a key factor. You know, you don't think about it at the time how important it is, but just the fact, I think we had a unique situation at Marshall. I don't think I don't think the other centers were probably as fortunate as we, as far as, in fact, I think Johnson Center, I don't know that they have hardly any sort of intercommunication, you know, with the people. And to some extent, the Cape has a little bit of that. But I think we have by far a better situation right here in Huntsville.
Y'all have that unique bond because you shared that unique experience together.
Yeah. Right.
That's
Yeah.
great.